Yes, I guess recording is started. So, welcome to all of you for the second session of Aspen Simulation Software, a basic course for beginners. How many of you are joining this session for the first time? I can't. Okay, there are three. So, okay, let me first introduce myself. Uh, So, let me first introduce myself. I'm Prasil Kapadia. Currently, I am pursuing my PhD from IIT Bombay. I have completed my BTech from SVNIT Surat in 2019. And during that time, when I was in final year, final semester, we learned a very basic on Aspen Plus. Then I joined Reliance Industries Limited at Jamnagar, and there I used Aspen for the simulation of two major problems. One was to increase the design capacity of high purity isobutylene plant, and second to check the condensate hydraulics for the condensate system. There, I used Aspen. After that, I joined IIT Kharagpur for my masters, and I worked with Professor A.K. Jana. And there also, for my MTech project, I have used a bit Aspen. So let's get started. So yesterday in last week's session, we preliminarily focused on some basic parts of Aspen, and we started with uh, simulation of flash dump. So today we will start with distillation column. So before starting, let's have some discussion. What is distillation column? Why do we use distillation column? Anyone?
For separation.
Separation.
To
Okay,
separate a liquid mixture,
to
like
separate a
liquid
liquid
mixture.
mixture. Okay,
Mixture.
to separate a liquid mixture. Okay, then
Yes.
anyone?
To separate a liquid mixture is depend upon boiling point.
Yeah, separation based on boiling point, that is important. Anyone else? How many of you have joined? Currently, I can't see the number. Okay, 17. It's
To
okay
separate a number of components
to separate a
from
number
the
of
original
components
yes,
from the
from the
original
original mixture.
mixes. So okay, so the distillation, guys, just a minute. The distillation column is used for the separation of more volatile component from the less volatile components. And the distribution of these components in two phases. One is liquid phase and one is vapor phase. This distribution is basically governed by VLE relationship, that is vapor liquid equilibrium relationship. So everyone knows distillation column has a reboiler. So what is the use of reboiler? Reboiler partially vaporizes the liquid received from the bottom. From bottom section, we receive less volatile components. So to partially vaporize it, reboiler is used. And from the top, we are using reflux. So part of condensate is withdrawn from the top product, and the rest is fed to the column as a reflux. So this is the schematic of distillation column. Here we can see that, I guess you can see mouse cursor. Okay. So feed is entered before entering the distillation column. Based on our requirement, we can preheat the feed. If it's required, we can preheat the feed. To here, feed is first sent to a exchanger where the feed is preheated, and then it is entered to the distillation column. So this part of column is called feed tray location, the where the feed is entering. Then from distillation unit, we will be obtaining more volatile component from top and less volatile component from bottom. So this one is reflux drum. The part of liquid is sent back to the distillation column and the other is withdrawn as a product. Similarly for condensate stream. So can anyone tell me what will be the pressure here? Let's say at point 2, after point 2 pressure is P1, and here at P3 location the pressure is P2. So what should be the condition? P1 should be greater than P2 or P1 should be less than P2?
Less than
Sorry,
P1 less than P2.
I'm not able to listen. Can you repeat?
P1 less than P2.
Anyone else?
Excuse me, sir. Have
Yes.
you
Can you
shared
repeat the
a screen?
Uh, Please one by one. Hello.
Did you share the screen?
question?
Oh, you guys are not able to see my screen.
Because
Oh, I'm
I'm not able.
sorry. Oh, I'm sorry. I did not share the screen. I'm sorry. Wait. Oh, I will re-show you everything then. Wait, it's taking time.
Thank you, sir.
You can see now.
Yes, sir. We can see,
Yes,
sir.
we can
Oh,
see.
I'm
Yes.
sorry. Please, someone remind me if something like this happens. So
Yes,
again,
sir.
I will show
Sure.
it to you. The distillation column. The distillation column works on separation of more volatile components from less volatile ones, and the distribution is given by vapor-liquid equilibrium relationship. We have one reboiler and we have one reflux drum. Reboiler is at bottom to partially vaporize the liquid product obtained from the bottom, and reflux, a part of condensate is withdrawn as a top product and the rest is fed to the column as reflux. So here, this is the feed. First we are preheating the feed and then it is entering into a distillation column. So what I was asking, at feed it is the pressure is, let's say, P1, and here at the feed tray location the pressure is P2. So what should be the condition? Hello, please someone
P1
respond.
is greater.
Could you repeat again? Could you please repeat
Feed is
again?
more.
Uh, Please one by
Feed
one.
pressure is more.
P1 is greater than P2.
P1 is greater than P2. Feed pressure should be greater than that this pressure. Similarly, let's say what should be the pressure at top and what should be the pressure at bottom. Which should be higher? P2. Let's say at top it is P2 prime and at bottom it is P2 double prime. What should be higher? P2 prime or P2 double prime?
P2 double prime higher
P2
Pressure at
double
the
compared
prime.
to
bottom
P2.
is more,
Yes.
while
Pressure at the
pressure
bottom.
more than pressure at the top.
Yeah, correct. Now let's say the this after this condenser, the stream leaving, sorry, after this reboiler, the stream leaving here and the steam entering, which temperature should be higher?
Temperature at the bottom is higher.
No, this temperature, the temperature leaving the reboiler stream or the temperature that will be entering the reboiler stream, which one should be higher?
Leaving the reboiler stream.
Leaving the reboiler stream. Okay, let's say which temperature will be higher at top or at bottom?
Bottom is higher.
Bottom is higher. Okay.
Bottom.
Okay, so this is distillation column. Let's see how it works. So the more volatile components, what is okay? We will see what is volatility. So the more volatile component, and let's understand in a simple way that the component that has lower boiling point. So the component that has lower boiling point, what will happen? It will easily move from liquid phase to vapor phase, correct? So what will happen if it is moving easily from liquid phase to vapor phase? Its concentration will gradually increase in vapor phase. Correct. So this is how we obtain more volatile component in vapor phase. So the more number of trays and the more reflux ratio, the better is the separation. So to increase the product quality, we should have more number of trays and more reflux ratio, but not more like some abrupt value up to a point. Okay, so can anyone tell me what is the difference between evaporation and distillation? Evaporation also the feed is heated and it is evaporating. So what is the difference between evaporation and distillation?
In
Anyone?
evaporation. Hello.
Yes. Are
In
you getting some
evaporation, the
disturbance from back from in my side? Or is it fine?
mm, it's fine.
Okay.
It's fine,
So
sir.
May I speak?
okay. So can anyone tell me the difference between
Uh,
evaporation and
in
distillation?
distillation, we do have simultaneous condensation and evaporation.
No, that is not evaporation actually. In distillation, there is no evaporation.
Vaporization, sorry, on each train.
In in distillation, both the components, all the components are present in both the phases. While
Both
in
the
evaporation,
phases, meaning,
means
yeah,
liquid phase
evaporation
and
also, yes, evaporation also something is evaporated. So something is in vapor phase, something is in liquid phase.
Distillation is liquid-liquid, evaporation is liquid-solid.
No, not exactly. You
Hello,
guys are wrong.
Evaporation
hello.
is used for the increasing concentration, and then distillation is used for separating the component.
Okay, increasing concentration. So let's say feed concentration. Okay. Anyone else?
Sir, evaporation we are using mainly when the volatility difference between two or more two components is very high.
Yeah, exactly. When we use evaporation, the volatility difference between two components is very high. Or we can say that one component is extremely volatile and the second component is more or less non-volatile. In that case, we vaporize the feed and we vaporize we boil our whole solution and the less volatile is vaporized. So can anyone tell me the example of evaporation? If you have learned
Con-
this distillation chapter from BK Dutta, anyone?
con-
Yes.
Concentrating like orange juice.
Yeah, exactly. Anything else? Any other example?
making of salt from seawater.
Okay, correct. Okay, so you understand the difference between distillation and evaporation. So relative volatility. So what is relative volatility? It is the concentration ratio of A to B in vapor phase divided by the same ratio in liquid phase. So concentration of A to B, Ya by Yb in vapor phase. Y represent vapor phase in our whole upcoming every sessions. Y means vapor phase and X means liquid phase. So Ya by Yb fraction of A in vapor phase by fraction of uh, concentration ratio of A to B in vapor phase divided by Xa by Xb concentration ratio of A to B in liquid phase. So let's say relative volatility of A is greater than B. So what should be the value of alpha? It should be greater than 1, less than 1, equal to 1. Anyone?
Greater than one.
Why greater than 1?
Because why
Yeah,
concentration
you are
is
correct, Sid. Yeah.
concentration of A is more than B in vapor phase.
Okay, we will obtain more concentration of A because it is more volatile. That's why alpha is greater than 1. So if we convert this equation, we get y equal to alpha x by 1 plus alpha minus 1 into x. I am 100% sure most of you have used this equation during your mass transfer course. Am I right?
Yes, sir.
Yes. So, okay. So before going for this shortcut method, let me know which methods you have used during your undergraduates for designing of a distillation column.
Macabee method.
Okay, McCabe-Thiel method. Anyone else? Anything else?
Sir, we are using FUG method for calculating a composition during multi-component distillation,
Okay.
and uh, or also we are designing the diameter of distillation column using uh, flooding velocity concept.
Okay. Yeah, that is a different concept, but that is correct. Anyone else? Someone has used Ponkan-Savariate method?
Microphilly method.
Yes, McCabe-Thiele
Yes,
method.
sir.
Other Ponkan-Savariate method.
Confluence. Yes, sir. When the assumptions which are taken in the McCabe methods, those
Yes.
assumptions are not taken during the development of uh, trays in Pontryagin Severage method. So we use that method.
I'm sorry. Can you please repeat?
Yes, sir, we are also using that Pointwell separate method in which the latent heat of condensation and latent heat of vaporization is different in different trace.
Okay.
And Molar
S-
fluoride is also not equal in each trace. It's constantly
Okay.
changing.
Okay. So have you guys plotted X versus Y, then XD, then design the number of stages? Have you done it on graph paper
Yes, sir.
No,
Yes,
sir.
sir.
using
Graph.
mag?
The makeup
So,
fill, so we draw makeup fill, but the Pointwell separate we don't draw.
yeah, that is more painful. So both methods are more rigorous methods, but let's say I want to start with zero. I don't have anything. So at that time, before going for this complex calculation, we can start with a shortcut method. This shortcut method is FUG method. Anyone knows the full form of FUG? I am sure the one who said that FUG
Fenske under
method.
root.
Fancy
Fenske under root Gilliland.
and
Okay, Fenske. What does Fenske? mm, What is significance of
ideal
Fenske
number.
in this? Number of trays. Okay, then Underwood.
Minimum number of trays.
Yeah, minimum number of trays. Underwood
Reflux
Reflux
ratio.
ratio.
Reflux ratio.
and Gilliland.
Or
Reflux. Actual number of stages.
Okay, let's see. So, in this shortcut method, first what we do, we perform material balance. Okay, before going to this, why I'm teaching this shortcut method? Because in Aspen Plus, we have used or you have used this DSTW model, right? So this model works on this, not exactly FUG method, but it works on a Wien Underwood Gilliland method. So it is just Fenske's equation is modified to calculate minimum number of trays. So we can simulate our system easily, but I want you to show the I want to show the actual theory of FUG method. So that's why before going for simulation, I will be first showing what is FUG method. So in FUG method, as step one, we are given a problem statement. So from that problem statement, we are supposed to perform material balance. So from material balance, we know the composition of top and bottom. We know the composition. I mean to say is we have some target, like I want to achieve 95%, 98% pure products. So we know the individual flow rates and we know our targets. So from that we can perform material balance. Then I will be coming to step two. Step three, everyone knows this equation, right? And minimum is equal to ln yd 1 minus xb 1 minus yd divided by alpha average. So this alpha will depend on temperature or not? Will this alpha be dependent on temperature or not?
Yes, sir. Depends.
Okay, it will be dependent on temperature. So to use this equation, we need to know the temperature of top and bottom. So so we need to perform calculation of temperature. So for that, the top temperature is given by summation of yi by ki is equal to 1, and bottom temperature we estimate temperature by summation of xi into ki is equal to 1, and we take value of average alpha by geometric mean alpha top into alpha bottom raised to 1 by 2. So this deep Richter chart, I will show that to you. So this is deep Richter chart. Everyone can see, right?
Yes, sir.
Yes, so you have pressure, you have temperature, and this chart is available for some hydrocarbons. So you can estimate temperature. You need to first guess the temperature. For that guess temperature, you need to check the value of K. And for those values of K, summation of yi by ki should be equal to 1. Whenever that yi by ky is equal to 1, that is our top and that is our top temperature and corresponding water temperature.
uh,
So from
what
this,
is Ki here?
ki is yi by xi.
Okay,
We
okay, so
know
thank you,
in
thank you.
last from last lecture. So we use this alpha average and we estimate minimum number of trays. Now, this is the step 4 to find the value of theta. And from that theta, we can estimate our minimum. So before going to theta, can anyone tell me what is this Q? Equation of Q line, if anyone has studied during your...
Slope of feed line.
I'm sorry,
Feed line.
I'm not able to clearly listen to you. Can you repeat, please? Hello?
So it's the fraction of liquid in a feed.
So what is the meaning of Q is equal to 1
That means saturated liquid,
and Q is equal to 0?
superheated,
Saturated
saturated
vapor.
vapor.
Saturated vapor. So let's say in your problem statement, it is given that your feed is saturated liquid. So what will you take? Q is equal to 1 and you will solve this equation and you will get some value of theta. And then you will put this value of theta. You will put this value of theta in this equation and you will estimate minimum number of minimum reflux ratio required. Now, from the minimum reflux ratio, by using Gilliland correlation, this is the plot. This plot is given in Cedar and Cedar book. If anyone has used this book, or there is one correlation also available, but that is a complex equation. So this is the plot available. N minus N minimum by N plus 1 divided by R minus R minimum divided by R plus 1. So from this relation, you can calculate actual number of trace and reflux ratio required for your distillation column. Then to estimate the feed tray location, this equation is used, that is NR by NS. So NR is number of stages in enriching section and NS is number of stages in stripping section. Enriching section means top section or bottom section?
Top.
Top section.
Top section. And NS is number of stages in stripping section. This high HK means heavy key component. Heavy key means the component that has lower volatility, and low key LK means low key component. So the component that has higher volatility. So from this equation, you can calculate the ratio of number of stages in enriching section and number of stages in stripping section. Let's say I have NR by NS is equal to 1.5 and total number of stages is 30. So how can we calculate feed tray location? Anyone? Hello? Yes? Anyone?
So we got the total number of stages, which is n. So nr plus ns is equal to n, and we have the nr by
Yes.
ns relation.
Ratio. Okay, let's say I have required 10 trays in stripping section. So my 11th will be feed tray location, correct? So from this shortcut method, we can estimate minimum number of trays, minimum reflux ratio, and from that actual number of trays, actual reflux ratio, and the feed tray location. This is when we don't know anything, this is the way we can start. Okay, so now let's solve a problem. So first I will show how to solve a problem like last time, and then one of you will share their screen and show everyone how to solve it. So let's first start this problem. So let's first read the problem. A feed stream consisting of 60 mole percentages of ethane and 40 mole percentages of ethylene enters a DSTWU column having a flow rate of 200 pound moles per hour at 75 Fahrenheit and 50 psi pressure. This feed is required to fractionate in a distillation column capable of recovering at least 99.6% of light key components. So we are just giving the condition that I need 0.996 recovery of light key component and 99.9% of heavy key component in the bottoms. The sample process operates at 300 psi with zero day-to-day pressure drop. So there is no pressure drop in our distillation column, and the column is operated at 300 psi pressure. The pressure in reboiler as well as condenser is same. there is no need to write this sentence because it is already written that there is no pressure drop. So whole column will be at 300 psi pressure. In the simulation, use total 30 theoretical stages, including condenser and reboiler. So applying RK property method, simulate this column and calculate required parameters. So first let's start ethane and ethylene we have. I guess you can see, right? Hello? Anyone
Yes, sir.
please respond? Yes. Okay. So first I will search ethane. We have ethane and ethylene. Okay, there are so many ethanes. Okay, let's go for this equals option. Ethane. Yeah, ethane. We will add this. Okay, it is added. Now, second one is ethylene. Ethylene. Add. Okay, we have added both the components. Now let's move ahead. Next. So which property method we are supposed to use? We are told to use RK equation of state. So let's go for RK is not here. So we'll go from method name. Here you will find RK. RK equation of state. Okay, so we have added it. Now we don't need to do anything. Now we'll go for simulation. So in separators, sorry, in columns, this is DSTWU that we are supposed to use. I have used DSTWU, materials, okay. We will align blocks. This is just to look our simulation better. Line blocks. Let's say this is one is feed, this is top, and this is bottom, or let's say distillate and bottom. Now, %60 ethane and 40% ethylene. So we are given mole fraction. Mole fraction 60% ethane, 40% ethylene. The temperature is 75 Fahrenheit. 75. Don't forget to change your unit. Fahrenheit. Then 15 psi and 200 pound pulse per minute. 15 psi and our unit is pound mole per hour. Correct? 200 pound moles per hour. Now, okay. So how many number of stages we are told to use? 30. So 30 number of stages with pressure is 300 psi of both top and bottom. 300 psi. psi. Now we are told that the distillation column capable of recovering at least 0.996 of the light key component in distillate. So can anyone tell me what will be our light key component? Ethane or ethylene?
Ethane.
Are you sure?
Ethylene.
Ethane or ethylene?
Ethylene.
Ethylene.
ethylene. Correct. So in light key, we will choose ethylene. We can change these names also. And 0.996. Okay. So here heavy key component will be ethane. So what will be the fraction here? Hello, anyone?
Point not 4.
0.004. Please be careful here. This key component recoveries is from top. So if you choose light key as 0.996 with ethylene, so automatically you need to have x1 plus x2 is equal to 1. So the rest will be ethane. Now, okay, we are set. So let's run our simulation. Is anyone simulating with me? Okay, I guess no one.
Yes.
Who is this? Can you tell your name?
This is Herschel.
Okay. It's taking time. Is your simulation done or Harsil?
Yes, I guess so.
Okay, I don't know why it's taking time in my case. Okay, whose mic is on? Harsil, where are you right now? It seems you are at a good place.
Yes, I live in a really good place. It's a company colony quarters.
Where? Which company?
Atul Valsad.
Oh, you are in Atul Valsad. What are you doing right now? Means you are a student or?
No. I am working as a process engineer in a
Oh,
joint venture
great.
company of Atul.
Oh, great, great. One of my friend was in Atul. He left in, I guess, 2021.
Okay.
I'll pause this. I'll stop
Another correct?
this. I don't know. It's taking longer than usual. Okay, I don't know. It's not working. Harshil, can you share your screen and show everyone what have you got?
Okay.
It's not. In my case, it's not. It's taking time. I don't know why. Okay, I have stopped sharing my screen. If you have done it,
Yeah, sure. Is my screen visible?
yes, your screen is visible. It's okay. Go below and show mole fractions. Okay, so we can see that in bottom there is, yeah, it's correct. Bottom we have 99.7 mole percent of ethane, and from top we have 99.4 mole percent of ethylene. Wait, let me check. 99.6. I'm getting 99.6 from my. Okay, yeah, it's visible for me now.
I have selected the RKSOA method.
Yes. Yeah, it's correct. It's correct. It's correct.
Sir, ethane should be on top.
Sorry. Yeah, you're correct. Ethylene is 99.4 and ethane is 99. Okay, can you go and show us what are the minimum number of trays required? Minimum reflux ratio required? Okay, go to results part of that block.
Yes.
here. So minimum reflux ratio is required as 7.3 and minimum number of stages as 29. 30.
Yes.
Okay. Results. Wait, I am also having that. Okay. So, okay, you can stop sharing your screen.
Okay.
Ashil, I ask you one question. From which college you are?
I'm sorry. Who is this? First,
Uh, uh, Fasil, Fasil sir. Hello.
hello. Yes, Abhijit.
Sir, I have a doubt. When we looked at this table, na, sir, there was a distillate temperature negative. Why?
Yeah, that is coming as negative. That is not our concern right now because we are willing to obtain ethane also. So ethane's
Okay.
that point will be lower. That's why we are getting negative point, negative temperature. Someone was asking something before that, Abhijit. Want to repeat or should I move ahead? Okay. Um, so we can see here that what we did, we just provided flow rate, our feed composition, and we just told that I need minimum this number of I need minimum this percentages of purity. So from this much, this minimum data, we use shortcut method and we estimated some minimum number of trays and minimum reflux ratio required. Now let's go ahead for red flag model. So we will continue the above problem with a few modifications. A hydrocarbon stream, same problem. A hydrocarbon stream consisting of 60 mole% ethane and 40 mole% ethylene enters a red flag column having a low rate of sorry, it's flow rate, not low rate. Flow rate of 200 pound moles per hour at 75 Fahrenheit and 15 psia. The distillation process that has a total 68 theoretical stages, including condenser and reboiler, and a total condenser operates at same condition 300 psia. The distillate rate, reflux ratio, and feed tray locations are given. So use same RK property method and first estimate the compositions. So anyone wants to do it or should I show you? I'm sorry, I'm not able to follow you.
I can do it.
Okay, you go ahead. Abhijit, what's your surname?
Shirsagar.
Okay, you go ahead. I will stop sharing my screen. Say first, say everyone what you are doing.
Pardon?
Discuss what you are doing. At least so
Yeah.
that this
My
method
screen,
you are using.
my screen is visible.
Yes, yes. The method is RK Swift, not SRK.
Okay. I will just RK stop.
It won't be go for method name. There you will find it. Not base method. Not in base method.
Okay. Make that.
Yes. R will be on top a bit. Yeah, RK Swift. Okay. You have added components, right? Ethane and ethylene.
Yes, I have it.
Okay. Okay.
Now we will add column
Okay, which column you will add? Red flag.
red flag.
Okay, go ahead.
Okay, now we will add components. Feed. Feed.
Okay,
Okay.
feed.
Top product.
Be careful here. Just delete that stream first. Wait, just
Sorry.
delete it. Read what is written there. Wait. Yeah,
Second
what's
liquid.
written? Liquid
Second
or
liquid.
water distillate.
Yes.
Okay, then here, what's written? Yeah, there.
Liquid distillate.
Liquid distillate and on top vapor distillate. So we are using a total condenser. So we will be following for liquid product.
Liquid product. Now we will add bottom.
Yes. Is this fine for everyone? Like one is solving the problem or should I solve?
So
Please
we have
respond, guys.
added feed, distillate, and bottom.
Bottom. Okay.
Stream
Now,
flag.
yeah,
Now we
now
will
we are
add
supposed to give. Yes.
feed flow rate, feed composition.
Yes. So feed flow rate is 200 pound moles per hour. Yeah, it's on mole basis, but it's in pound moles. Pound moles per hour.
How much it is?
200.
300.
200. 75 Fahrenheit pressure.
$50.
And 15 psia.
Okay.
Composition mole fraction. It is 0.6 ethane and 0.4 ethylene.
So we have added temperature, pressure, and molar flow rate and composition of the feed rate. Now we will go next.
Wait, you are doing a mistake.
Okay.
Retrofit used.
Yes.
It's mole fraction. Please be careful.
Yes.
It's mole fraction. Go to mole
Yes.
flow part, please.
Right. Okay. Step by step. Now we can go next. Right. Number of stages 16 or 68.
61, I guess. 41. 41. Then, okay,
Total
condenser.
condenser.
We have total condenser.
Total
Reboiler we won't touch. Phases, we have vapor liquid phases. We won't touch it. Just keep it the way it is.
for liquids. Convergence standard.
Yeah, we won't change convergence. What is convergence criteria? Anyone? Means why we, what does the mean, the word convergence mean?
Tolerance for our answer.
Yes, tolerant. Okay. Distillate rate I will give you. We are given two conditions. Distillate rate is 79.8 pound moles per hour. 0.8 and reflux ratio on mole basis 8.75. On mole basis. Okay.
Yes.
Now go to next. Now it is told that. Oh, I'm sorry. Can you go to configuration? The total number of trays are 68. I'm sorry, it's 68. Okay, and at streams 41 above stage. Feed tray location is 41 above stage.
Okay, what about stage?
Above stage. Okay. Now go to next. Pressure is 300 psi A. Okay, now run it. You will get a warning. You will get a warning message. I hope.
Simulation errors. Warning, one warning.
Yeah, warning is there. Let's ignore warning for now. We'll see what is the warning. Go to results part. Stream results, yes. And see what is the composition. Mole fractions. So bottoms, we are getting 99.6 mole percentages of ethane. And from top, same, we are getting 99.6 mole percentages of ethylene. 99.6 or it's 99.7, 99.63. Okay, whatever is the answer. So now go for the warning. What is the warning? Sorry?
It's control panel.
Yes.
Feed
Go ahead.
pressure.
Yes.
Warning is feed pressure 0.10342 into 10 raised to 6 of
Feed
stream feed.
pressure of stream
Is
feed is lower than stage.
stage
So what did we learn? Feed pressure should be
higher.
higher than
Column pressure.
column pressure.
मतलब
So
feed
let's go now again go to that flow sheet part. Change some pressure. Our feed is I guess at 15. So go for 14.5 and see what happens. So you should understand warning also it's not completely correct. You are getting some warnings in your simulation. Just I guess some yeah, okay. No, not in feed. In distillation column. You need to give column pressure to some value.
block, column,
Yes, column.
specification.
Go to pressure. Let's say 14.5. Right, 14.5.
Stage 2 pressure.
No. Stage 1 pressure only. Just change that 300 psi. We have given 0 pressure drop, correct? So
Oh,
at all
right.
stages, pressure will be 300.
14.5.
14.5. Yeah, now run it. Wait. First reset it. Were you here in last class? I guess you were there.
Yes, reset before running.
Yes. Now run it. Now tell me, are you getting any errors?
No results available. No error.
Yeah. So now our simulation is correct. Okay, you can stop sharing your screen. Thank you
Oh,
for sharing and showing everyone this problem.
thank you.
Everyone understood or not? Please respond. Harsil,
Yes, sir.
The video lag.
sorry.
Video is lagging.
Okay. Okay. So now I will share my screen. Okay, there were some issues like the column that I simulated, the first with DSTWU. These were the conditions 70 Fahrenheit, 15 psia. Okay, yeah, here it's mole fraction, not mole flow. Okay, now it's correct. Okay. So we were asked simulate the column and compute the composition of top as well as bottom products that we did, right? Okay, is there any discrepancy in product or compositions obtained from red frag and DSTW columns? If yes, what is the main reason? So this is the composition that I have written. So there are discrepancies, right? Hello.
Yes, sir.
There are discrepancies, right? Very small, like 0.001.
Mhm.
So what can be the reason? What can be the reason? DSTWU
Just
is a shortcut method, while RedFrag performs rigorous calculation. So the results obtained from RedFrag will be more accurate than DSTW. Both are different methods, so there will be a little discrepancy, but DSTW is just a shortcut method. So rigorous method, RedFrag will be giving us better and accurate ones. Okay. Okay. Let's move ahead. Okay. Does anyone know what is mercury tree efficiency? I will not ask definition. At least tell me yes or no if you have heard
Ye-
this word.
Yes.
Yes. Okay. Want to respond? What is mercury tree efficiency?
stage efficiency.
Not exactly. Okay. So let's say on a tray, liquid is entering and vapor is leaving. This is what happens on a tray. Liquid will enter and after equilibrium, vapor liquid equilibrium, vapor will leave the tray. Let's say the vapor leaving the tray is not in equilibrium with Xn. Let's say Yn, vapor fraction is not, vapor composition is not in equilibrium with liquid fraction. So this will be the case most of the time. So in that case, we will be using mercury tree efficiency as Yn minus Yn plus 1. That is actual values we are getting divided by Yn star. Means what value we would have obtained Yn star equilibrium value, but we are not obtaining that. So ideal condition Yn star minus Yn plus 1. This is called mercury tree efficiency. So the higher the mercury tree efficiency, we will be approaching closer to the actual separation. Our actual separation will be closer to the ideal separation, the way it would be. So let's say in the last problem. Okay, let's go to next problem and see what is mercury efficiency. A multi-component distillation column specified in the figure, this figure, that has total number of 20 stages, including a condenser and reboiler with 60% mercury tray efficiency. A hydrocarbon feed mixtures enters above the tray 10 of the red flag column. Apply Peng-Robinson equation of state and consider 120 psia pressure throughout the column. So we are supposed to simulate the column. Anyone wants to share their screen or should I show it to you? I will guide how to add mercury efficiency. Anyone? Guys, please respond. Should I solve or anyone wants to volunteer? I will guide.
You do it, sir.
Okay, I'll do it. So, wait, I need to close this. Okay, so this is the problem statement that is given to us. Propane, C3 means propane, IC4 means isobutane, NC4 and butane, isopentane and N-pentane. So first I will add all the components. Propane, then isobutane, N-butane. Okay, N-butane is not showing like this. Let me just write butane or one butane. Yeah, N-butane, add N-pentane, and isopentane. It's not showing isopentane. Okay, let's search isopentane. If anyone able to see, stop me.
Put dash pentane and then search. It will come.
Iso dash. Who was this? Abhijit, I guess. To methyl butane. Okay, so I will just rename these whole streams. C3, rename I, C4, rename C4, rename P5, rename and I, P5, rename. We'll go to next. We are told to use Pang-Robinson equation of state. So we'll just choose Pang-Robinson. Now we'll go to next. It will give us interaction parameters. We will just use that. We'll not modify anything. Okay. Now let's go to simulation. In simulation, we'll be going to columns. We'll be using red frac. Same thing. Then, okay. Let's see the question again. So here in this case, we are not using a total condenser. We are using a partial condenser. So a fraction of vapor is leaving and liquid is entering to the top. So here it will be from here and bottoms. Okay, everyone understood or not?
Yes, sir.
Yes, sir.
Line blocks. Bottom. Okay. Let's enter feed conditions. Temperature is 12 Fahrenheit, 120 psi. 12 Fahrenheit, 120. I guess it's 120 psi A. And mole fractions 100 pound moles per hour. 100, and this value is pound mole per hour. And we'll be giving mole fraction. I guess mole fraction is given in the question. Now mole fraction 5, 15, 20, 5, 15, 20. Then isopentane is 25 and n-pentane is 35. So 35 and 25. Okay. So the total is 1. We are correct. Now let's go to next. Okay. Minimum number of stages. How many stages? 20 stages. Correct? So 20 stages. Condenser is a partial condenser. Partial vapor because we are getting product as vapor only. Then everything else is fine. Now, okay. Which flow rates are given? Vapor flow rate, distillate flow rate is given, and reflux rate is given. So distillate flow rate is 50 pound moles per hour. 50 pound moles per hour. And reflux ratio is not given. Reflux rate is given. Reflux rate is 125 pound moles per hour. 125 pound moles per. Correct. Now go to next. So what is feed tray location? Feed tray location is 10 about tray 10. So above stage tray number 10. Now
Sorry,
pressure.
this above stage. Hello.
Sorry, yes.
So this above stage means the filter is 11.
No, like this is the 10th tray. So on the okay, above means 11. Yeah. Yeah, yeah. Below means below and on the tray means on the tray number 10. This is above tray, above 10. Condenser pressure is given as 120 psi throughout the column. 120. You need to change the unit to psi. Okay. So we are not giving any pressure drop or something. So it means that there is no pressure drop in the column. We will not add mercury efficiency first. Let's see what are the results we are getting. Then we will add mercury efficiency. I hope it won't take infinite time. Okay, results are available. So streams. Mole fractions. Yeah, we are getting some values. Right? Now, this is what we will obtain if our mercury tree efficiency is 100%. But our trees are not efficient. So what will happen? Product quality will reduce or increase. If we will
Reduce.
be now going
Reduce.
for reduce. So let's say product quality is reducing with reducing mercury efficiency, and I want the same product quality now. So what should I do?
Increase more number of stages.
Increase more number of stages. Correct. Okay, now let's add mercury efficiency and see what happens. So wait, I'll show you. This block is B1. So in B1 block, there is one point of efficiency. Click there. Which efficiency we need? We need mercury efficiency. Specify mercury efficiency. So from column number, from stage number, how many stages were there? I guess 20 stages. So we'll exclude reboiler and condenser. 2 to 18 for the stage number, stage starting at 2 to stage, sorry, 19, not 18, 2 to 19. The stage efficiency is 60%. Okay. Let's see first what were the original results. We were getting 64.8% pentane from bottom and 39.9% butane from top. Now let's we change the efficiency and see what happens. Yeah, the value has changed. It's 63 and 39.3. So if I want the same efficiency, then I should increase the number of trays. Correct? Now, what was the second question with this? Simulate the model and calculate the product compositions that we did. Now, produce a temperature versus stage plot. I want to see on all 20 stages, what is the temperature. So anyone knows how to do it? I'm not getting any response. Please say yes or no.
No.
No. Okay. So let's go. Go to this block B1 part. Then wait, yeah. In B1, wait, I will show you. Yeah. In B1, block B1, go to analysis. What do we need? We need temperature profile. So I will just click on temperature from top. So this is the temperature that we are getting. Temperature profile. Is procedure clear to everyone?
Yes, sir.
Yes, sir.
So bottom has lower temperature, top has high temperature. Now let's say I want to, what else we can plot? Let's see. We can plot pressure also. Pressure, what should be pressure? Should be same. Because we have given
efficiency.
no, we have given zero pressure drop. We have given zero pressure drop. We have told that we have told in our question that the whole column is operating at 300 psia pressure. I can change the units from here also. Yeah, so it's at, sorry, it's 120, not 300, 120 psi. So pressure is constant throughout the simulation. What else we can see? Flow rates we can see, K values we can see, relative volatility we can see. It will ask for a component, let's say C3. Okay, C3 is the lighter component, that's why it's reference component. So there its relative volatility they have taken as 1. What if we see some composition C3, composition of C3? So in bottoms, it's negligible. It's highest on top. So I guess you understood how to play with this tools. Am I right? Anyone wants to ask anything? How to do it? I guess it's clear to everyone.
Yes, sir.
Abhijit, yeah.
Yes, sir.
Harshil.
Yes.
Okay. So this was all about distillation column. Now let's move towards liquid extraction. Uh, does anyone know what is liquid extraction? When do we use liquid extraction? Basic. Okay, no one wants to
Like
say.
in gas sweetening,
Sorry.
To say,
in gas sweetening we use TG or MEG liquids to absorb. No, that is gas.
That is
Gas and
gas absorption.
to separate a component from a liquid mixture
To
using a
separate
third
it.
component from a
Okay.
liquid mixture using a liquid, another liquid.
Okay. I will come back to your point in some time. You will have to answer. Okay. So what we
Used when
do?
the boiling points are very,
Sorry.
it is used when the boiling points are very near to each other. So that distillation is very expensive in that case.
Okay. I will come back to you too. What's your name?
Vaishnav.
Vaishnav and Abhijit. I will come back to you, both of you. Okay. So liquid extraction. Everyone knows what is liquid extraction. Feed is brought into intimate contact with a second immiscible solvent in order to achieve transfer of solute from a feed to solvent. Let's say I have some feed. Feed contains two A and B. I want to extract A from B using C. So in this case, we used we use liquid extraction using a solvent C to extract A from our feed. So why have I used word this immiscible solvent?
Because we don't want to use any kind
So
of
that the loss
energy.
of
We can
solvent is
separate.
One by one.
We don't want to use any kind of energy such as heat for separation of two
Let's say my
liquids.
solvent is soluble in feed. What will happen?
uh, uh,
We
three
form single
solution,
phase.
three component solution will be formed, which will make the process
Yeah,
uneconomical.
we are not solving problem. We are creating more problem by adding solvent if we are doing this, right? So
I mean,
the solvent should be immiscible. Now the two liquid phases are then separated. Let's say solvent plus the A that we wanted to separate from feed. So A and C we have, then we can separate A and C, two liquid phases. Extract and raffinate phase. Extract is the solute rich phase in solvent, and raffinate is feed stream with very little amount of solute left. So question, when to use LLE? Okay, as I promised, I will come back to you guys, Vijit and Vaishnav. So Vijit, I have, let's say, a liquid mixer containing C3 and C4. So will I go for liquid extraction or will I go for distillation? And should I say what should I do? Should I go for either of two? How can I say that?
Uh, if boiling points are very near, so we
Okay.
will definitely go for extraction.
Uh, so,
Okay.
so we will go for a distillation for a particular reason because C3 and C4 both will dissolve in organic compounds such as ether, chloroform, etc.
Okay. Let's say I'm giving an example. Like I am having a stream that contains benzene plus some traces of water. So what should I do? Benzene and water, they have relatively good difference in volatility. So if we are going for distillation, we will be easily able to separate them. Benzene plus traces of water. Please listen to my words very carefully. Benzene plus traces of water. So what should we do? Distillation or liquid extraction?
We should do liquid extraction because benzene will get dissolved in a organic solvent and it will be much cheaper compared to this.
Let's say I am not going for some organic solvent. I'm going for some ionic liquid. That's different kinds of solvent. Let's say I'm going for ionic liquids. So that organic solvent part is solubility part is resolved. Then
If we need purity more, then we will go for distillation, high purity.
okay, just think one thing. You are having a huge volume of benzene. Okay, in that huge volume of benzene, you are having a very little amount of toluene, a very little amount of water. What will you have to do if you want to go for distillation? What will you have to do?
So like we have to provide more energy in terms of energy to like separate benzene and water in that case.
Yeah, in that case, we have only
We
traces
have
of
to use
water.
extractive distillation.
Sorry, can you repeat?
Sir, we have to
Vaishnav?
do extractive distillation, sir.
Extractive distillation. Okay, we will not go for extractive distillation right now. That's a different concept.
But it it majorly depends on the what is how much is the purity we required
No,
of
no,
the end product,
no.
because
Puneet,
distillation is usually last operation.
Puneet, can you explain your answer a bit more?
Like sir, for in case we have trace amount of water, let's say 1% in and rest 99 is benzene. So like
Yes.
we have to separate that 1% more energy would be required for, in terms of distillation when we do distillation.
We will have to boil up our first mixture. So it will create a huge amount of, what we are doing, we are giving huge amount of energy just to vaporize water. We want to separate benzene and water. Water is in a very trace amount. And what we are doing to remove that trace amount, we are providing extensive amount of heat in distillation column. Is this feasible practically?
No, sir.
Anyone? No, this is
No.
not possible.
No,
So
no.
the case is where we are having in one major solution, from one major solution, we want to remove something that is in less quantity. In that cases, we go for liquid extraction. Understood or not?
Yes, sir.
Yes, sir. So
Yes.
solvent we discussed. Solvent. So what should be solvent? What should be characteristics of solvent?
First, it should be
To dissolve
non-miscible, sir.
the extract the water.
One by one. Okay,
To extract
Vaishnav,
water.
you say first.
Sir, it should be non-miscible. It should be thermodynamically stable. It shouldn't react with the solution.
Yes. Yes, correct.
Highly
It should have a good
highly
solubility
selective.
also.
Sorry, one by one, please.
Highly
Okay.
selective.
Yeah, it should be highly selective. Okay, so is it clear when to use distillation and when to use liquid extraction?
Yes.
Yes.
Yes, sir.
So anyone from Gujarat here?
Yes, I am from
Yes.
Gujarat.
You
I
know
am
this.
also.
You know this proverb like બકરું કાઢવા ગયું અને ઊંટ ઘૂસી ગયું. That will be if we go for distillation. घर में से बकरी तो निकल गई बट बकरी निकालने के लिए ऊंट डाल दिया और अभी घर में से ऊंट कैसे निकाले दैट इज अ मेजर प्रॉब्लम. Okay, so I hope you understood when to use liquid extraction and when to use distillation. So this is one schematic. I have taken this from standard book BK Datta. So feed containing A and C, we are adding it into extraction column with solvent B. We will see why solvent is also having A and C. So with solvent B, we are extracting C. So B plus C and some amount of A will be there. And now we have to separate B and C. So solute is separated using some distillation or something else and solvent B. So solvent B, we will recycle it to our via our extraction column. Correct. So this is the process we follow. Now, which unit is this? Is this co-current or counter current?
Counter.
Counter current. We are adding feed from stage number 1 and we are adding solvent from stage number n. So those are in counter current mode. So material balance, this thing you have studied, I guess, in mass transfer operation 2, liquid extraction. Okay, so I am not discussing theory for this part as I assume that everyone knows.
Yes, sir.
These are just material
Yes,
balance
sir.
equations. You need to plot those ternary diagrams, then curve to find minimum number of trays. Okay,
Yes.
so let's take one example. A mixture of water and methyl ethyl ketone is to be separated using a third component. The feed mixture enters at 1 bar pressure and 25 degrees Celsius with composition of 78% of water and rest MIK. So tell me, 78% water is there and only near to 20 to 22 percentages of MIK is there. So if we go for distillation, what will happen? We'll have to provide huge amount of energy to separate water, separate MIK that is in little quantity from water. The pure solvent, the solvent is N-octanol. I have not mentioned it here. The pure solvent N-octanol enters at the same condition as feed with 100 kg per hour. Countercurrent extraction unit contains 10 theoretical stages. Calculate the amount of MEK extracted. Use Unifac model. Plot ternary diagram. Anyone attended my last lecture last Monday? Why are we
Yes.
using Unifac model here? I guess I mentioned last time.
More accurate result.
Yeah, more accurate. That is the safest answer. Yeah, correct. Unifac is more accurate for liquid activity coefficient calculations. Not methods, where are components? Yeah, components first we need to add components. I will delete all these. Delete. So I have water, MEK and solvent is N-octanol. Okay. Water, was it N-octanol or N-octanic? And wait, I will check what was the solvent. Just give me a minute. I guess it is N-octanol as far as I remember. Water, then MEK. Methyl ethyl ketone, and just wait for a minute. Yeah, it is octanol, N-octanol. Okay, so octanol. One octanol. Add. Oh, I have added that 2 times to remove one. Now go to next. This is a liquid extraction. Wait. I need to change property methods. First, methods specification. We are going for Unifac. Unifac. Now go to next. No. Okay. Now let's add. Yeah, from here only. I guess it's this unit only. Extract. One feed. This will be water plus One will be water plus MEK and other will be solvent. We will obtain one extract phase, that is solvent rich phase, and one raffinate phase. Correct? Okay. Now I'm just increasing this line blocks. Yeah. Okay. So I'll just change these names. Feed, S stands for solvent, extract, and raffinate. Okay. So now let's go for feed condition first. What is feed condition given to us? 1 bar pressure, 25 degrees Celsius temperature. 1 bar pressure, 25 degrees Celsius temperature. And 96 kg per hour. 96 kg per hour. So we'll change mole to mass kg per hour. And we are given mass fraction. Mass fraction of 0.781 water. 781 water. Mass fraction. 0.781 water. In our feed stream, octanol is 0, right? So I'm just writing 0 here. So it will be 1 minus 0.781. How much will it be? Point 0.22. Approximately 0.22. Correct? And it is in mass fraction. Now let's go to next. Now solvent. Solvent is also entering at same condition. 100 kg per flow rate of mass flow rate of 100 kg per hour, 25 degrees Celsius, and 1 bar pressure. And that is pure. Octanol is pure. So its mass fraction is 1. Now let's go to next. Now, how many number of stages we are told to use? We are told to use 10 theoretical stages. We are not going to specify any temperature profile or heat duty, so it's just adiabatic. There is no heat loss. We are assuming. Now, in one liquid phase, okay. What should be in one liquid phase? One should be rich in octanol, and one should be rich in water. Correct?
Yes, sir.
Octanol means
Yes, sir.
solvent rich phase, and one means one water rich phase. Now let's go to next. Pressure. What is pressure? There is nothing told to us. So let's assume that pressure is 1 bar only. Okay. Here streams. Feed is entering from stream number stage number 1 and S is entering from stage number 10. So this is counter current operation, correct?
Yes, sir.
Correct? Yes. Okay, next. What is left? Okay, temperature also we will give 25 degrees Celsius. Now let's run our simulation. Oh, we are having some errors. Total flow of L2 components log bypassed. Okay, I guess issues are here in temperature and pressure. The components is correct. Water 10. Pressure is 1 bar, right? Yes. Mm, we have made some mistake. Wait, let me check. This one is problem number 7. There is some error in our feed condition only, I guess. Is anyone able to run correctly? Okay, no response. I assume everyone is seeing. Just a minute. Okay, let's just check these conditions. Everything else is correct. 10 stages. We need one water component and one octanol component. This is also correct. Streams 110. This is also correct. I don't know why it's not running. We have added octane or it's octanol. Wait. Components. Specification. Yeah, it's octanol only. It's correct. Water. Just give me a minute. Sorry, guys. Hmm. It's still processing. I have results available here. Let it process first. Oh, it's taking time. Let's still then see the results from here. So we'll go to result summary, streams. One is extract and one is raffinate. So first I want to show you these mass flows.
Sir, you take octanol mass flow rate as a 1.
Okay, it is 1. Okay, it's my mistake then. It should be 100, not 1. I have taken 1. It's taking time, guys. Were you able to run it correctly? Hello?
No, sir.
I don't know it's still running. Let's check condition from here only. So feed is, there is some issue in condition. 25 degrees Celsius, 1 bar, 96 kg per hour flow rate, and mass fraction is 0.781 water and 0.219 MEK, correct? Then solvent, it is 25 degrees Celsius, 1 bar, 100 kg per hour. And oh yeah, here it should be 0.1,
Mass
not,
fraction 0.1.
it should be 1, not 100. Okay. No, but I have chosen, okay, it's mass fraction only. Wait, where am I going to run this? No, this is not even running. Hmm. Guys, it's taking time. Can anyone share the screen and do it? I will guide to you. Anyone?
Sir, it should be 100. So it was one.
So mass flow rate is 100. That is correct. Mass fraction is 0.1. Can anyone share the screen? Actually, my Aspen, it's not working right now. Anyone? Abhijit, can you
Yes, yes, sir.
please do it? Wait, I'll stop sharing my screen. If my results are available, I will stop you. No, it's still processing.
Is it visible? Screen?
Yeah, it's visible.
No.
Oh, you have
No.
to start from 0. Okay.
Yeah.
I hope.
What should
Okay, do it. If you want to do it.
I will like to do it, but
No,
it's not same thing. Let's try.
Yeah, there are some issue in condition only, I guess. Nothing else. My Aspen is not.
Why it is restarting? Simulation.
New simulation. Then
Yeah,
go
but
for.
there is another window open. Okay. Yes. No. No. Same problem here. It's hanging. Okay. What are the components? Hello.
Hello, yes. What are the components? Water, MEK,
Water.
and ethanol. MEK and
Octanol.
ethanol. Just write MEK, it will show.
Octanol, right?
And octanol. One
And
octanol.
octanol.
No? One.
Yes. Octanol. No, you won't be able to write whole. You will have to search.
Okay. Octanol.
Octanol, yes. Yeah, go for one octanol. First one.
So we have added all the components, right?
Yes.
Water, MEK, and one octanol.
Octanol. Yes.
Now next, we will use unifact method.
What's your name? Abhijit. You can
Uh-huh.
stop sharing. I have results available.
Okay.
I'll share my screen. I guess it was some issue. I don't know what was the issue. Screen. Okay, can you see my screen?
Yes, we can.
Yes. Okay. So let's go one by one. For feed, we have given correct condition like 25 degrees Celsius, 1 bar pressure, 96 kg per hour. Water is 78.1 and MEK is 21.9. Then solvent stream, that is 100 kg per hour mass flow rate, 25 Celsius, 1 bar, and mass fraction is 1, that is pure. Then specifications, 10 number of stages. Then one is, I guess it's issue here. First liquid phase, it is taking water. No, but it should not be like that. One is water rich phase and one is octanol rich phase. Then feed is entering at first and 10. So this is counter current operation. Pressure 1 bar. Temperature was also 1 bar. So I will reset. No, I will not. I am not running it again, else it will it will not run. So Abhijit, can you try without sharing screen? So here we can see that uh, so in problem statement, let's see, water was 75 kg per hour and MEK was only 21. So the quantity of MEK is considerably less in water. So we should not go for distillation operation. We should go for liquid-liquid extraction. So using solvent S, we are getting out of C in feed 21 kg per hour. MEK was there and we are getting 100% MEK in extract phase. That is 21.024 kg per hour in extract phase. We are getting some amount of water that we will always get. And in raffinate phase, we are getting majority of water 66. A few amount of solvent will be there and very negligible amount of MEK. So, okay, did you understand concept and did you understand how to use this? Please respond, anyone.
Yes, sir.
And why we
Yes,
go
sir.
for liquid-liquid extraction. Okay, now we are told to plot a ternary diagram. How many of you have plotted ternary diagram on graph paper using pen, pencil? At least I have plotted it. Anyone? All of you may have
Yes,
done
Yes.
sir.
it.
Yes, sir.
Yeah. So, uh, yeah, I will just, did you understand what did I do? I switched from simulation to properties window and then I went to analysis like last time we did TXY, PXY diagram similarly. And I will just choose ternary diagram. Okay, where can I see my diagram? Run analysis. So this is ternary diagram and there are timelines. This we have done in your theory. So I will not explain what is ternary diagram. Okay, so this was all about liquid-liquid extraction part. Is it clear to everyone the difference between distillation unit and liquid-liquid extraction unit?
Yes, sir.
Only one is responding. Anyone else?
Yes, sir.
Sir, can you explain the number of plates you expect you deducted
I'm
to
sorry. I'm sorry. Can you be a bit loud?
during
C2, yes.
distillation? During distillation, you have deducted two stages from 20, but you
Sorry,
write
I'm not.
19.
I'm not
Which
able to
means
listen to you. Can you type your question in chat box? I'm not able to listen to you clearly. Can you type? Harshil has raised his hand. I assume he has understood everything. Or are you having any doubts?
No.
No. Okay. Okay, let's write him. Okay, let's wait for his question. Actually, I was going to teach gas absorption part also, but we are not having enough time today. So, okay. Now, how can we proceed further for separation of MEK from N-octanol? We have this, we had these results, right? Uh, Streams in extract phase, we have mole fractions. Let's go for mole fractions. 0.5 octanol, 0.3 water, and 0.1, 0.2 MEK. Now I want to separate MEK from octanol. So what should I do now?
Distillation.
How will you design distillation column? Respond. How will you design distillation column? We learned today.
Shortcut method or red
Yeah,
track
first
method?
we will go for shortcut method. We will find minimum number of trays, minimum number of reflux ratio required. And then by using those output parameters, we can design actual column using red frag model. Correct? Can you guys do it?
Yes, yes, we can.
Yes. So actually, I I was going to teach this gas absorption part also, but we'll see this next time. Gas absorption, it will take some time. And I was also going to show you heat exchanger, but these two we'll keep for next time. So let's revise what we did today. Do you want to go for this gas absorption part or next week, as you guys say?
Next week, sir. Next week.
Okay, today it is actually enough, right?
Yes, sir.
Okay.
Sir, am I audible? Hello.
Yes, you are audible.
My question is that, sir, in distillation, there is
Yes,
20 traces, right? And you
there is.
reduce two traces.
Wait. Sorry. There is in distillation. There is
20 trace, 20, 20 trace.
where.
Oh,
Hello. Yes.
in distillation problem, there is 20 trace, right? The last problem.
Wait. I will open this last problem. You need problem statement. Yeah, this one.
Yes, there is 20 trace, right? 20.
I am sorry. I am not able to understand what you are saying.
Ye-
Can you type
Yes, yes, there
or
was
any
20.
He's saying 20 stages.
Yes, yes, there
20
was 20 stages.
stages? 20 stages. Okay. Now, say ahead.
And sir, you reduce two stages, but you write 19. I don't understand this.
In Murphy tray efficiency.
No, sir, you didn't
Yes.
consider reboiler there, no? That's why.
I'm
He's
sorry.
asking.
Okay.
He's asking in trays. Why did you write 19 stage when it is given 20 trays in problem? So
Oh,
we
no, we added. Yeah, that is including reboiler and condenser. I guess 20 is including condenser and reboiler.
yes, right.
That's why we need to write. I guess I have written 20 only. So please take care. It's my mistake. I guess you need to remove two stages. It should be 18, not 20.
And you write 19. 19.
We considered a condenser as a stage, sir.
Condenser and reboiler are also stage. Like say, I am starting from bottom. So reboiler is 1, then 2 to 18, 2 to 19, and then 20 is condenser like that. So when we provided mercury tree efficiency, it was for 2 to 19. We are not providing any efficiency for reboiler and condenser. I hope whatever you ask, it's clear to you. Or send me an email if it's not clear. Okay, let's go to some problems. Simple questions. Someone is saying something? No.
Sir, in extraction, solvent
Yes.
name is not given.
In
Hello?
extraction? Yeah, in extraction.
Solvent name is not given. So on what
Yeah, it is.
basis we have choose
No. It is
octanol?
octanol. It is octanol. I forgot to write in question. It is octanol.
Okay, sir.
From the book that I have taken the problem, octanol, but I forgot to mention the name in problem statement.
Okay.
Okay, let's start some simple questions. In Aspen Plus, which unit operation is commonly used for separating components based on their boiling points?
Distillation.
Correct. Then what is the purpose of reboiler?
To heat the liquid.
To heat the liquid. Then what is the function of condenser?
To cool and condense the
Condenser
vapor.
condensed.
To cool and condense the vapor. Now, next question. What is the purpose of the absorber in an absorption? We are going to see next class, but if anyone knows.
Option
To
C.
remove gases
Remove
from
gases
vapor.
from vapor.
This is from vapor.
Yeah, someone just mentioned that CO2 absorption using methyl monoethanol amine. Who was that? Okay, no one will say their name now. Next.
CO2 absorb
Yes, you
carbon
mentioned
cap.
only, right? You only mentioned, right? Okay. Liquid extraction in Aspen Plus is primary preliminary used for. Where are we using liquid extraction?
C. Extracting one component or more components from.
Extracting one or more components from a liquid phase to another when we are having that component in less quantity. Then what is the rule of settler? Okay, you guys know what is mixer settler? Okay, wait, I'll show.
Separation on based on density.
Yes, wait, I'll show that to you. Mixer settler, I guess it's
Type
there
of
in this.
decanter.
Sorry?
Type
I,
of decanter.
yeah, I guess it's in 423. Mixer settler is there. So in mixer settler, it is one single stage liquid extraction unit in which what we do, we add solvent and our feed, we mix it, and then we allow it to settle down. So when it settles down, it's in two phases. One is extract rich phase and one is raffinate phase. So that is mixer settler. I guess it's not here. Yeah, this mixer and settler. See, in mixer, we are adding our feed and solvent. It is mixing. This is a single stage operation. Then we are passing it to a settler. So on settler, based on density difference, one will be heavier phase and one will be lighter phase. So we can extract it. So for this question, the settler will be to separate the phases based on the density differences. Now in Aspen Plus, the term solvent in extract LLE means
Liquid phase in which extraction occurs.
B option.
yes,
Option B.
liquid phase option A
B.
or
B.
B. Yeah,
B.
the component that is being extracted is solute, not solvent. Then what is the key factor influencing the number of theoretical trays in distillation column?
Reflex
Flux ratio.
ratio.
Yes, we I show you that graph n minus n min versus r minus r min, right? So n and r are interdependent. Next, which parameter is crucial for designing an efficient liquid extraction process? Yes, anyone?
Solvent to feed ratio.
Yeah, it should be. Yeah, it should be solvent. No, it will not only depend on solvent flow rate. It will depend on both feed and solvent flow rate because we are extracting something from feed using solvent. So we should consider both solvent and feed flow rate. So the solvent to feed ratio. This is how we write material balance FXF plus SYS is equal to E plus R. So it will both depend on both feed flow rate and solvent flow rate. So solvent to feed ratio. Next, what does the term distribution coefficient refer to in liquid extraction? Have you studied this distribution coefficient?
Yes. Ratio of
So
solute concentration in two phases.
yeah, it is kind of not exactly kind of relative volatility, but it is YC by Y means solute in extract phase divided by solute in raffinate phase. So the distribution coefficient, higher the distribution coefficient, greater the extraction. Correct?
Yes, sir.
Next. Which of the following is a common solvent used in gas absorption? Okay, we are going to see this next class. Anyone?
Water.
Water, yeah. We'll see this next time. Which Aspen Plus tool is utilized for designing and simulating absorption columns? Absorption we are going to see next class. Answer is absorb. Heat exchanger also we are going to see next class. Okay. How can you estimate the reboiler and condenser duties in Aspen Plus? How can we estimate? It calculates by itself, but how does it calculates?
Energy balance.
Heat
Yeah.
exchanger
Yes, it estimates all these values, both duties from energy balance. Okay. You compare two simulations for the same separation with the different tray efficiencies. How would the results differ?
All.
How
High
all?
efficiency.
How
Higher
all?
efficiency leads to low number of stages. More the efficiency, number of stages will be minimum.
More the efficiency, equilibrium will be actual ideal equilibrium will be achieved.
Yes.
That's why we will. Yeah, go ahead. Then.
Higher
Yeah, please go
efficiency.
ahead. Yes.
Higher efficiency means we will get more
Higher
pure product.
product priorities for same number
Yeah.
of trays because we are actually achieving. Did you guys notice when first we used 100% efficiency, the purity was 64.8, and then we reduced mercury to efficiency from 100 to 60%, then our purity went to 63. So
Yes, sir.
higher the efficiency, higher the product purity, and higher the efficiency, lower energy consumption means we are using less number of trays, right? So we'll require less energy. One tray is removed. One or any number of trays are removed. So all are correct. Now next, what is the effect of increasing reflux ratio on purity of the distillate?
Increases.
Yeah,
Purity increases.
yes, purity
increases.
increases with increase in reflux ratio. How can you diagnose and troubleshoot flooding? Okay, someone told me that he learned this distillation column design, diameter, flooding. Anyone can respond?
Yes, sir.
Yes, sir.
Yeah,
Okay.
say
Flooding velocity.
yes, but how can you diagnose?
Increase
If there
the
is
pressure drop.
Liquid holder.
yeah, vapor holder, liquid holder, not vapor holder. Yeah, liquid holder. We'll check liquid holdup on each stage. If it's more than that tray spacing, like say this is one tray, this is another tray, and the distance, if the gap between trees is completely filled by liquid, it is called flooding. So we'll check liquid holdup on each stage if to troubleshoot flooding.
We can
Now,
also increase the diameter.
yeah, but once our column is set,
It means it in
yeah,
a steady state.
yeah, yes, while designing you can do it. While designing, it is some, I don't remember those calculations, but it was something you estimate some diameter and you need to take
Yes.
some percentages of that diameter. I don't remember those values.
Acre chart
Yes.
is there. We have to calculate the flooding capacity parameter. Then
Yes, yes, yes. Okay. Okay, what is the primary purpose of raffinate stream?
Excuse me, I have a doubt in previous
Provide
question.
solvent makeup.
Okay, sorry. Yeah, what is
Why
doubt?
can't the option be second option, increase the pressure drop across the column?
What will happen if I increase
Isn't
the
it?
pressure?
No. If the pressure drop is increasing across the column, then doesn't it indicate the situation of flooding?
Sorry, can you repeat?
No, I
No,
am
I missed.
saying is that if the pressure drop is increasing across the column, doesn't it indicates the flooding? If our vapor flow rate is very much, then the liquid will hold up in each tray. Then the column pressure drop across the whole column will not increase in that situation.
No, this is ask how can you die?
So
I'm
actually, it's asked
This is
no. You can
asking to
diagnose and
troubleshoot.
troubleshoot.
both are correct.
How can you diagnose? So diagnosis is a part. No, your pressure increase in pressure drop is a diagnosis, right?
no increase. Yeah, I'm listening my voice back. Can you first mute yourself? Okay, so you are checking the pressure drop across the column. I am not saying you should increase or decrease. Diagnose means what is the first step that you will take when this flooding will occur. So flooding is basically because of liquid flow rate. So you will check what is the liquid holdup on each stage. Yeah, pressure drop is correct, but we are seeing this effect because of that, right?
Can I say something, Prashil sir?
Yes, please.
Sir, question suggests that it is a packed column, and packed column is a continuous operation. So I think increase in pressure drop across the column will be the
Packed column is also there are two types of column, tray column and packed column. In tray column, we can have some flexibility with pressure drop, but in packed column, we can't have some flexibility with pressure drop because in packed column, some material is fixed within some, let's say this is our distillation column. So in some particular part, it is fixed. So we can't really play with pressure drop in packed column. Pressure drop will increase with time because of many factors in pack column. It won't remain constant like the way we can handle in this normal tray type columns, not in packed packed columns. Okay, I will get back to you with these questions again. I will see this again. Question number 18. Okay, so question 19, what is the primary purpose of raffinate? Okay, this is done. How can you diagnose and okay, this question is again repeated. So it's done. Thank you. Anyone?
Ex- like I had a doubt apart from what we have studied today.
Yeah, please go on. Who is this? Wait.
I am Puneet.
Puneet. Please say.
So like there is a scenario where we are mixing polar and non-polar solvent, as in there are mixture of two acid and one organic compound.
Two
And
acids. Wait. Mixture of two acid
and
and one
organic compound.
organic compound is not solvent, right?
So like let's say it's ethylene. So ethylene plus two acids is a mixture of this, and
Okay.
uh, and suppose we add an alloy to it, so there would be corrosion.
Alloy, it won't be liquid phase, right?
No. So like just like understand the whole
Okay,
problem
okay.
statement.
Okay, okay,
So
okay.
so like whenever we add alloy, there would be corrosion, and like small particles of it would dissolve in the solution.
Solution,
So
yeah.
in that case, if we have to estimate the properties of that liquid that we are dealing with, that is with what would be the variation in with temperature, or like that properties, sensitivity
Which
analysis,
properties? Which
sensitivity analysis,
no
or viscosity.
so see, I am a simulation person. So what I can tell you, you are having two acids and one ethylene solution, right? And you are
Yes.
ethylene in two acids or two acids in ethylene. Then you are using some alloy to extract
Yes.
what?
No, there is not extraction process. Just we have add
Okay,
an alloy, and that
okay.
alloy is like when it is dipped in acid, a few components would like come out. Oxidation process would take place, and then
On
it would,
alloy. Okay,
that like for example, we are taking an cobalt chromium alloy.
okay.
So like cobalt would form oxides of cobalt oxide and chromium oxide, and
Yes.
that would eventually dissolve in that solution. And this is an homogeneous solution.
Okay.
So for instance, if we have to do property analysis of this liquid, so we have electrolyte analysis in this Aspen. But like what all component should we take while doing this?
You should. I'm not actually getting your point. Means you want to simulate this thing in Aspen, right?
Yes.
Can you do it?
No, that's what, like I cannot do the whole process, but like for example, we have chromium oxide, cobalt oxide, that all component would be dissolved in the solution. So at particular time instant we can do. So like what would be the flow of doing this?
I guess. Uh, You need what I tell you. Your in your solution, cobalt oxide or chromium oxide, whatever you told me, that is being dissolving, right?
Yes.
I am not sure if you can do this exercise the way you told, like I can add manganese or whatever your alloy is, and you can see. But I suggest you can add some. You can add this chromium oxide in your feed only, and you can see the effect on. Okay, how can I explain this to you? Like
So
you take.
that's what I was telling. Like in component analysis, like when we add components, at that time only we need to add this cobalt,
Yeah,
chromium.
yeah, yes, yes, yes. At that time only. At that time only.
Okay. And like method of what type of estimation should we do? Electrolyte.
Method I will have to see. I have not deal with this kind of metals part. I guess electrolyte will work,
And
but it's
like
liquid solution also. So you will have to choose some. I'm not sure what property method it's you should take.
because for simplification, I told only two compounds because the alloy is mixture of 7 to 8 compounds, and each 7 to 8
You
compounds will
can't.
give.
Okay, I was suggesting you can't take. If you can't take everything, go for some two or three major and
Okay.
see its effect on solution. What I am suggesting, I don't know if it will work or not. Just in Aspen, just take uh, solution in some composition like two acids and ethylene in some composition, and directly add MnO2 there and see uh, what is heat capacity and whatever property you need to see. But whatever composition you are taking, will it actually, will that composition be actually achieved or not? That I'm not sure.
Okay.
Where are you working? This seems industrial or research problem.
Yes, I work in industry.
Where?
It's a medical industry.
Okay, where? Location?
Surgeon Medical Technology.
Location.
Surat.
Oh, you are in Surat. Where are
Yes.
you in Surat? Wait, let me first stop this recording. Stop recording. Stop.